So we're going to deal from point B to point C, where we have 0.8 x, and the other limit is 3.2, right? So I'm going to again sketch. So this is your point A. Okay. Now you have a point B over here. And this has a value of, I think, 120. Okay, 120 times 10 to the power 3. Distance, this is our x. V as a function of x again. Moment as a function of x. Geometric datum is at point A. So the equivalent load over here is 50 times 10 to the power 3 x. Okay. Then the associated distance from here to here is x over 2. Right? And the distance from here to here is 0.8. And then up to here is x minus 0.8. Those are the distance. So you have to ensure that you get the distance right. So again, we apply static analysis. The magnitude of forces in the y direction is equal to 0. So now you have 120 times 10 to the power 3. Okay. Then you have minus 50 times 10 to the power 3x minus v as a function of x is equal to 0, right? So v as a function of x is equal to minus 50 times 10 to the power 3x plus by 120 times 10 to the power 3. Okay, so this is your equation number 3. Again, we're going to take moment in the z direction at point x is equal to 0. So from here, we are going to take the moment at the dot I'm going to draw. Okay. So the 120 is going to generate a clockwise. So minus 120 times 10 to the power 3x. In fact, it's x minus 0.8. Then you will have the equivalent load doing a anti-clockwise direction rotation and multiply by x over 2. Okay. Then plus, let me see if I can shift this so I can write it on one line, less confusing. Then plus by m as a function of x is equal to 0, right? So now expand the term, so it's minus 120 times 10 to the power 3x minus is plus 120 power 3 multiply 0.8, 96 times 10 to the power 3, and then you have plus by 25 times 10 to the power 3 x squared plus by m as a function of x, whole thing is equal to 0. So m as a function of x will be equal to minus 25 times 10 to the power 3 x squared plus by 120 times 10 to the power 3x, then minus by 96 times 10 to the power 3. Okay, this is equation number. So now we have, I'm going to bring the table across, right? So we will have minus v as a function of x is equal to minus 50 times 10 to the power 3 x plus by 120 times 10 to the power 3. And then we have a moment equation. And this will be equal to the entire term over there. Okay. I'll just copy and paste. I need more space. Not enough space. Okay. So the process will repeat itself. Okay. I'm just going to write the rest of the equation down. So at point C is a constant. Okay. So this will be equal to positive 32 times 10 to the power 3. And then from C to D, V as a function of x is equal to minus 40. M as a function of x now is equal to minus 40 times 10 to the power 3 x plus by 160 times 10 to the power 3. And then we go back to 0, 0. Okay. As I said, the process is very repetitive. Okay, I'm not going to go through them. Okay, but those are the exact equations or constant. So now we are going to sketch the shear force and bending moment diagram. Okay, we're going to sketch it now. So we are going to have, first we're going to draw our shear force diagram. And I'm going to help you check whether is your shear force and bending moment diagram, does it make sense? Okay. And I believe we covered all this in 2P04, but 2P04 was done so long ago, so it's like a revision for you all. So we have our, okay, so do I have space? Yeah, I do. So V times 10 to the power 3 Newton is our shear force, so it's 80, 60, 40, 20, 0, minus 20, minus 40. Okay. And we have our x-axis. So this is 0 0.8, 1.6, 2.4, 3.2, and 4.0. Okay. So this is our x. Okay. As I said, 0 is always on the left-hand side, right? That's why all our geometric datum is on the left-hand side of the beam. It does not move at all. Okay. So let's focus on the shear force. At 0, we have 0. What you see over here from A to B, 0.8, we have a linear equation. Okay. Minus 50 times 10 to the power 3. Then it goes down to, sorry, yeah, it goes down to minus 50 times 10 to the power 3. So it will, if you were to plot this out at 0.8 or 0.779, right, you will have minus 40. And how do you get minus 40? If you look at minus 40, or the equation is minus 50, times 10 to the power 3 multiplied by 0.8. This is equal to minus 40. Okay. So this is your diagram over here, or your line. And then exactly at point B, we jump up to 80. Okay. So it goes straight up to 80. Now, for this reason, that's why when we divide our section, we have to divide at point A to B, point B, B to C, point C, C to D, D. If I've not got point B, right? If I've not done point B, you will not know that this is equal to positive 80. Right? Because the function from A to B is minus 50 times 10 power 3. That's why you have minus 40 over here. And then at point B, we calculated it's exactly at where? At 80. Okay. Then the next one is minus 50 times 10 power 3x plus y 120. Okay. And then when x is equal to, at point C at 3.2 is minus 40. So we know that this is over here, minus 40. Then we draw a straight line. Right. And then from 3.2 to 4 is at minus 40, then it goes back to 0. Okay. So this is at a straight line. And then this goes back to 0. Okay. Now, one thing I like to highlight is the shear force diagram, okay, intersects the 0 line at 2 points. What do I mean by that? At 0.8, it intersects at 0 shear force. At 2.4, it also intersects the 0 shear force. Okay, I want you to take note of this line or these points. Okay, so what I propose is we go for a 5 minutes break. We come back and I will continue. Okay, I will stop recording. We'll come back in 5 minutes time.